or it has to be sorted already, right?
Yes.
Yeah. So once we have a guarantee that a given list is sorted, then we are able to use a binary search. And this slide is just saying that binary search is just faster. Right? So real life example would be, how do we look up on the you guys don't know what a phone book is, do you?
No.
Do you guys know what a paper dictionary is?
Yeah.
Yes.
You do? Okay. All right. So when you look up a word in a dictionary, what do you do first?
Like we find like the first letter it starts with.
Exactly. And that you can. Oh, Ron, you're smart man. So you just said that you would look at the first letter of the word you want to look up, right? And
Yeah.
you can do that because the dictionary is sorted, right?
Yes.
Dictionary is in an alphabetical order, sorted, right?
Yeah.
You don't have to think about, oh, where is K? Or is it after A? Is it before B? Because we know that we're guaranteed that a dictionary, any type of dictionary, is sorted, right? And
Yeah.
instead of remember, Ron, you said in linear search you would have to start from the beginning until you find the item. So in a linear search, if you were to look up a word in a dictionary, you would start from alphabet A, right?
Yes.
But we don't have to do that because we know the first letter of it and we know the dictionary is sorted. So instead of just going from very beginning, you just have to go to the letter, and then from there you're gonna. And once again, after the first letter, the second letter is also sorted in the dictionary, right?
Yes.
So when you decide to, so in, let's say you're looking for a word called ubiquitous, and you would obviously go first for the first letter, which is a U, and then after that, you would obviously be inside the part of the letter U. You would decide to go whether after or before the pages, right?
Yes.
Yes.
And that's binary search. So we're gonna look at this together. So I know this is this is an animation of a binary search. So let's say you have a list, right? And what you want to do first is you want to cut the list in half, and this is an example. So let's say search the following array A for 36. Let's say let's look for 36 right together. And what you want to do is you want to cut the list in half, right?
Yeah.
And you're gonna continuously cut the list in half until, because you went rightward, because we know 36 is greater than 19, right?
Yes.
Yes.
From here you cut the list again, and obviously the half is here, but you see that the 36 is still greater than 32. So you're gonna cut the list once again, which would be the middle value, where the middle value would be 37. And you notice that 37 is greater than 36, and there is no 36 in the list. So
wait, isn't it just finding like a median? So we're finding a median of like a
Yes.
number set. Yes, and so we got a like quadrant 3, and to compare, is it out the quadrant 3 or in the quadrant 3, and to get the value.
right. Yeah, that's exactly correct.
Okay.
All right. Okay. So, all right. And that's binary search. And let's go back to our Runestone textbook. So they call it, so linear and sequential are interchangeable words. So sequential search means linear search. So don't get confused by that terminology of it.
Okay.
All right. Linear search or sequential search. We talked about sequential, linear search, and both binary search. And All right. Here, I want you guys to open this page. I'm gonna post it on Slack and do the questions below.
Okay.
I did. Is
Mm,
this one, then
And check your answers. And
yeah.
and if you get anything wrong, let me know.
okay.
Binary search.
And unordered.
Smallest number of letters.
For searching starting. Which one? Binary search. Mm,
Okay. Last one.
which? Mm,
A sorted list of a number of 500 elements is closest to the maximum number.
mm, mm.
Okay.
Sorted list of number contains 500 elements. Which of the following maximum? That will be examined. I'm confused with question 5.
All right, we're gonna do it together. So, and you got everything else all right?
Yes.
Okay. Smart man. You guys are. How are you feeling about computer science so far? It's only our second week, isn't it?
Yes.
Yes.
But we don't you feel like we've learned a lot?
Yes. Yeah, I think I didn't know it. Like if we do the question like 2 classes or 3 classes ago.
Yeah,
before
exactly.
we started. Yes.
And now you guys are getting more comfortable with Java as well, right?
Yes.
Because remember in the beginning of our core class, you guys learned about Java, but I think we code a lot more in my class, right?
Yes.
Yes.
And like I promised in the beginning of our class, I will guys make you experts in Java. All right, shall we go over the questions?
Yes.
All right. Is everything okay except number 5?
Yes.
Okay. All right. A sorted list of numbers contains 500 elements. Which of the following is the closest to the maximum number of list elements that will be examined when performing a binary search? So let's look at this together. So let's say what this question is asking is that, let's say you have a sorted list that contains up to 500 elements. And which of the following is the closest to the maximum number of list elements that will be examined when performing a binary search? The maximum number means what's the worst case scenario that you will have to look for a value inside the list. Do you guys understand the question in the first place, or are you still confused with the question itself?
Like a little bit with the question.
Okay, all right. So in the binary search, we said we're gonna cut. The first thing we're gonna do is cut the list in half, right?
Yes.
Yes.
And let's say we had 7 items. And what's the value in the middle then?
It's
4.
4.
And let's say you're looking for and we gotta decide if we wanted to go towards left or towards right.
Right.
Right? Okay, so we are going right. So this was one step, right? It's one iteration. So we spent we had to look once, but we couldn't find it. So we're gonna do the same thing once again, right? Now that we have new list would be 5, 6, 7, right? And what do we do next? Cut the list, right?
Yes.
The value in the middle, which is 6. And 6 wasn't the value we were looking for. So we're going to cut the list again. But we only have 7 left in the list.
Yes.
And we found it, right?
So we are using like 500 to divide by 2 for several times to all the way
Right.
The closest to 1 or
Yeah. Exactly. But in this question, we don't know which number we're looking for, right? So the question is asking which of the following is the closest to the maximum number of list elements that will be.
So like the same thing as the 7, like as an example. So we are just finding like the 7. So we divide by 2 for several times from 500.
Mm-hmm.
It become like a 250, then 125, 62.5, and so
Mhm.
31.25. Then you have to divide by around like a 10 times to
Mhm.
get closest to 1.
Yeah, exactly.
Ah, okay.
Oh,
Because you would divide the list in half continuously. Let's say 500 divided by 2 gives you 250, and you want to cut the list in half again. It gives you 125, and if you divide it, you get 62.5, and 62.5 divided by, or 62 divided by 2 is 31, and 31 divided by 2 is roughly 15, and 15 divided by 2 is 7, and 7 divided by 2 is 3, and 3 divided by 2 is 1, right? So the maximum closest to the maximum number of list elements that you look at will be approximately 10, right?
Yes.
yes.
Yeah, this is how you would solve the question.
Oh,
Got it?
yes.
Yes.
All right, awesome. All right, so that was search algorithms and sorting algorithms. So another thing, I know I think our pace is super fast. So like so far, do you guys have any questions? Is there anything that you guys are confused with? You want me to clarify on?
No.
No questions.
All right, you guys are following super well. All right, so remember under the umbrella of algorithms, I said first searching is super important, and obviously sorting, the next thing that's as important as searching is sorting. And sorting means we want to arrange things in order, right?
Yes.
And we will look at a little. All right. You know what? Let's actually hold the sorting part for later. I think this is too advanced for now because we are also going to talk about. So in Java, we're going to talk about. I think it's better to talk about it in computer science A. So in Java, we're also going at some point we're gonna also talk about um, sorting here. Let's hold it for Java. All right. And now we're going to limits of we're going to go into analyzing algorithms, limits of algorithms and parallel computing, things like that. All right. Searching and sorting. So so how do you say which algorithm is better than another algorithm? So Ron, how do we know that binary search is better than linear search? Based on what can we say that?
Like if it's sorted,
Uh-huh.
then binary search is better than linear search.
Right, but why do we use the word better? Because it's faster.
But it's faster.
Exactly. So in computer science, we normally use the word efficiency of algorithms and how well an algorithm uses time and memory. So one thing we just said, what Ron said just a second ago was that it's better, it's because it's faster, right? And that's one aspect of efficiency of an algorithm in computer science. And the second aspect of efficiency in computer science is space, meaning how well are you using the given amount of space. Let's say you have what's the size of your iPhone, or if you whatever phone you have.
What size?
Yeah, The memory,
The memory.
the space.
Ah, yes.
Is it 256 gigabytes? Is it
64.
60.
okay? Okay. All right. See, so we are all given limited amount of space on our phones or computers, and we don't want to store everything we have into our phone because we have a limited amount of space, right? And how well you use the space, likewise, in programming is part of efficiency in computer science.
Ah, yes.
So reiterate, so the first aspect of efficiency in computer science algorithms is speed. So how fast or how faster is one algorithm than another algorithm. And the second part is how well does one algorithm use limited amount of space compared to another algorithm. That's efficiency in computer science.
Ah, yes.
Got it?
Got it.
Yeah.
All right, perfect. All right. An instance of a problem also includes specific input. Yeah, so an instance of a problem, we don't have to actually know the definition of it, but